Hi, my name is Siena, and in this project, I'll be exploring 5 tools and techniques in design and manufacturing that stand out to me. The topics I will be exploring in this project are transfer molding, incremental forming, acoustic emission, lathes, and reconfigurable machines. Let's dive into each and see why these are important in the field. The first topic I will cover is transfer molding. Transfer molding is a manufacturing process commonly used with electronic components and rubber and silicone parts. For this process, an uncured thermosetting material is placed in a heated transfer pot or chamber. After the material reaches the proper temperature, it is injected into heated, closed molds. Depending on the type of material used, a ram, plunger, or rotating screw feeder forces the heated material to flow through the narrow channels and into the mold cavity. Because of internal friction, the flow generates internal heat, which raises the temperature of the material and homogenizes it. Curing then takes place by cross-linking. Transfer molding is used for many industry applications, such as aerospace, oil and gas, semiconductor, pumps and valves, reciprocating compressors, power generation, renewable energy, and the hydrogen industry. I find this process fascinating because of its ability to handle complex designs with high precision. It also utilizes internal friction for even curing, ensuring consistency in the final product. It is a perfect balance between detail and consistency, making it an ideal for mass production. Transfer molding has many capabilities and advantages. First is material properties. The curing process at high temperatures allows for excellent dimensional stability and increased strength of the molded parts, making them suitable for high performance applications. The second is intricate designs. Transfer molding is ideal for creating parts with intricate details, tight tolerances, and inserts due to the use of pressure, which ensures the material fills complex mold geometries. The third is reduced waste. Excess material often remains in the pot instead of the mold and can sometimes be reused, reducing overall material waste. The fourth and last is the high production rate. Although the setup can be complex, once operational, the process allows for a relatively high production rate compared to the other molding methods. The only downsides to this process are the higher mold costs and the potential material waste, especially in the channels used to inject the material. The next topic I will cover is CNC incremental forming. Incremental forming is a term applied to a class of processes that form a material in small increments. CNC incremental forming, also known as single point incremental forming, uses a CNC machine tool that is programmed to follow contours at different depths across the workpiece surface. The sheet metal blank is clamped and held stationary as the tool rotates. Tool paths are calculated in a similar manner as that for metal cutting, using a CAD model for the desired shape as the starting point. CNC incremental forming is ideal for sheet metal forms since they are especially well suited for applications requiring a compact and lightweight design. Sheet metal can be relatively thin while formed with features to make the part structurally strong and to also serve a performance function. Also, CNC incremental forming is typically used for rapid prototyping of sheet metal parts because there are no lead times associated with making hard tooling. I like CNC incremental forming because it's a simple process that's highly adaptable and doesn't require expensive dies or molds, making it a flexible option for customization and prototyping. I find it fascinating that so many complex shapes can be made with this process and just a CAD file. The main capabilities and advantages of CNC incremental forming compared to other methods are the high flexibility in shapes that can be produced and the low tooling costs. The main drawbacks include low production rates and limitation on allowable materials. Most incremental forming is performed on aluminum alloys with very high formability. My next topic is the acoustic emission technique. Acoustic emission utilizes a piezoelectric transducer attached to a tool holder which picks up acoustic emission signals, typically above 100 kHz, that results from the stress waves generated during machining. By analyzing the signals, tool wear and chipping can be monitored. Acoustic emission can be used to look for corrosion on the surfaces of various types of materials, coating removal of protective coatings put on materials, faults and defects for monitoring welding and other general flaw detections, leaks in pipe systems or storage tanks, and partial discharges from components subject to high voltage. Some of the most common applications for acoustic testing are airplane longevity estimation, bridge inspections, concrete corrosion monitoring, mine wall stability inspections, pressure vessel inspections, structural integrity inspections, and wind turbine inspections. This technique is really compelling because of its non-destructive nature and its variety of applications. It helps detect potential failures before they happen, which is crucial in many high-stakes industries. The science behind this method is also very interesting. I never would have guessed that sound could be used to detect faults. Acoustic emission has many capabilities and advantages. It gives you a direct measure of failure mechanisms, it is highly sensitive, it provides data immediately, it is non-destructive to the material being tested, it allows for a structure to be globally monitored, it can be used in hazardous environments including those that have high pressures, are irradiated, or have high temperatures, and it can be done remotely and detect defects in materials that might be hard to test using other non-destructive testing methods. Here are the main limitations for acoustic testing as a non-destructive testing method. Its usefulness is generally limited to locating a defect, not describing it in detail. That is, commercial acoustic testing systems can only provide qualitative estimations for the extent of damage found. It cannot detect defects that do not change over time. And it can be hard to use. Acoustic emission signals can be very weak, making noise reduction and signal discrimination crucial for accurate readings. I will be covering lathes next. The lathe is a very important machine to know how to operate. This machine rotates a cylindrical object against the tool that the individual controls. The work is held and rotated on its axis while the cutting tool is advanced along the line of the desired cut. The lathe is one of the most versatile machine tools used in the industry, and it is the forerunner of all machine tools. Lathe machines hold a vast array of applications across diverse industries. In the automotive sector, they are indispensable, used to manufacture numerous car parts, including pistons and cylinder heads. In the aerospace industry, they also heavily rely on these machines for the creation of intricate and precisely machined components. In addition, they are used to make musical instruments, gun barrels, and the creation of fine furniture, where intricate turning and precision is paramount. From shaping large metal sheeting in heavy industry to crafting delicate home decor, lathes reflect our world's engineering marvels. Their wide applications signify their integral role in pushing the boundaries of design and manufacturing. I like lathes because they're one of the oldest and most versatile of manufacturing tools, allowing for high precision and consistency in part creation. They have remained widely used after many centuries, and they have been innovated upon until we have the lathes we do today. With suitable attachments, the lathe may be used for turning, tapering, form turning, screw cutting, facing, dulling, boring, spinning, grinding, and thread cutting. Despite all the positive of lathes, they do have some limitations. First is required operator skill. Then there's setup time and potential for errors. There's also potential safety hazards in operating a lathe. And finally, there's limitation in the complexity of parts that can be created with a lathe. My final topic is reconfigurable machines. Reconfigurable machines support the rapid addition, removal, or modification of process controls, functions, and/or operations through reconfigurable hardware and software. They can be used to scale production capability and capacity. Reconfigurable machines are ideal in environments that need rapid production changeovers, like automotive or electronics manufacturing, where customization is frequent. They are also very beneficial in markets that closely follow consumers' wants and frequently introduce new products, like cosmetic and personal care industries. Reconfigurable machines are incredibly useful because they are designed for rapid adjustment of production capability and functionality in response to new market conditions. They can be used to decrease tooling costs, reduce lead time for new systems, and enable the rapid integration of new technology into existing systems. Reconfigurable machines have these key capabilities. Modularity. All system components, both software and hardware, are modular. Integratability. Systems and components are both ready for integration and future introduction of new technology. Convertibility. Allows quick changeover between existing products and quick system adaptability for future products. Diagnosability. Helps identify quickly the sources of quality and reliability problems that occur in large systems. And customization. It lets the manufacturer design the system to match the application. Some of the limitations of reconfigurable machines are that there is no standard design or principles to follow for making a reconfigurable machine. For a machine to be reconfigurable, it must be designed to be so. A normal machine cannot be turned into a reconfigurable one, so money and foresight will be needed to start the process of developing a reconfigurable machine that fits a manufacturing need. There aren't any standard approaches to identify root causes of component failure in reconfigurable machines either. In summary, each of these 5 topics offers unique advantages and capabilities, from the precision of transfer molding and the flexibility of incremental forming, to the predictive power of acoustic emission, the timeless utility of lathes, and the adaptability of reconfigurable machines. Understanding these tools and techniques has given me a broader perspective on the incredible variety of approaches available in design and manufacturing. Thank you for watching.